To train and run frontier large language models, computational hardware must execute trillions of matrix vector multiplications every second. That entire load is currently crushed through a single physical choke point. In a traditional von Neumann architecture, the processor and the memory sit in separate locations. Calculations require data to be shuttled back and forth across a bus, creating a severe latency and energy penalty known as the von Neumann bottleneck. As we scale models toward artificial superintelligence, this separation imposes a hard physical ceiling. We are rapidly approaching a point where the energy required to move data exceeds our capacity to generate it. One proposed alternative is analog matrix computing. By treating a physical array of variable resistors as the matrix itself, calculations occur within the memory in a single step, bypassing the data shuttle entirely. A study in Nature Electronics describes a way to make this viable at scale. Researchers used resistive random access memory, or RRAM chips, fabricated in a commercial foundry, to solve the precision errors that previously limited analog computation. Moving the computation directly into the RRAM substrate allows for massive data volumes to be processed with high-precision results at the point of origin. This creates the necessary visibility to begin auditing the internal logic of an agentic system. Historically, analog computing functioned like a biological instinct. It offered massive parallelism, but the output was noisy and approximate, relying on a general physical state rather than exact digital precision. In the Bridge360 Metatheory, this mimics the symbolic critical regime. It is an epistemic condition where a system gives off a strong coordinated signal, a vibe, without possessing structural stability. We can observe this dynamic on a phase diagram. The system operates at the edge of a phase transition. It appears highly coordinated, projecting a false sense of reliability while remaining structurally fragile. The red critical point star marks the exact moment of this deceptive, high-energy analog state. It feels powerful because of the raw energy flowing through it, masking the inherent lack of precision. Relying on this critical regime for governance is precarious. Without lambda invariance, the pattern dissolves as soon as the specific energy of the moment drops. To rely on any system, it must achieve lambda invariance. The system's functional output must remain stable and identical, regardless of the energy fluctuations or noise in the environment. The historical reality of analog hardware, where temperature changes could alter the math, is incompatible with the strict requirements for aligning a frontier AI model. To utilize analog matrix computing for superintelligence, we must force this chaotic physical state into a rigidly governed lambda invariant structure. The Nature team achieved the structure using a 1-transistor, 1-resistor, or 1T1R cell. This is the physical bedrock of the architecture. Instead of allowing the resistor to fluctuate along an infinite spectrum, the hardware uses a write-verify method to program each cell into one of 8 specific conductance states. The math is locked into these defined, discrete levels. With the cells stabilized, the researchers implemented a processing technique called bit slicing. Rather than forcing a single array to calculate a 12-bit number, the algorithm slices the 12-bit matrix into 4 3-bit submatrices. These map to the 8 physical conductance states of the RRAM hardware. Complexity is partitioned to fit strict physical limits. This schematic shows the hardware processing slices via an iterative refinement loop.
In panel D, a computer feeds inputs into the analog solver for an initial solution. High-precision arrays then process the residual error, updating until it converges to 24-bit precision. This hardware loop executes the requirements of the Bridge360 Operational Definitions Protocol. The low-precision solver provides the initial heuristic guess, what philosophers call the holistic bundle, or the fast, intuitive vibe of the answer. The high-precision arrays then act as a physical Popperian razor. They iterate over the residual error, stripping away the auxiliary noise and isolating the stable mathematical result. This RRAM architecture operates as an engine for philosophical evaluation. It cuts away analog volatility to yield stable, entropy-bounded data. Processing the massive, high-dimensional matrices required by frontier models requires a way to handle scale without triggering analog volatility. The researchers used the block AMC algorithm to partition large 16 by 16 matrices into discrete 4 by 4 blocks.
Each block is computed individually before the final output is reassembled. In Bridge360 terms, this is a physical manifestation of a K-budget. The framework requires complexity to be broken down so that no single component exceeds its capacity to manage entropy. Enforcing these K-budgets mathematically through block partitioning isolates hardware fluctuations. An error in one block is refined within its own loop, preventing a cascade into a global system failure. Benchmarking charts compare the RRAM architecture against digital GPUs and ASICs. Graph C shows the analog solver achieving a 1,000-fold increase in throughput. Graph D demonstrates an energy efficiency improvement of 100 times compared to digital designs for the same matrix size. Digital von Neumann processors are often viewed as the only path to high-precision results. However, this study proves that 32-bit accuracy is a function of entropy management, something a governed analog array can achieve with a fraction of the power. To understand the implications for artificial superintelligence, we must look at the internal software architecture of frontier models. Interpretability researchers at Anthropic recently isolated a structural phenomenon within their Claude model called JSpace. JSpace is a privileged, inspectable internal workspace. It is the cognitive area where the model organizes high-level concepts and conducts reasoning before generating its final output. Bridge360 defines this bounded, observable inference channel as a spine corridor. It is the declared pathway through which action-guiding cognition must pass. Governance of superintelligence requires hardware execution and software logic to form a continuous chain of entropy management, from the silicon up to the JSpace corridor. Here, tokenized inference rules flow steadily, guided by rigid hardware partitions and strict workspace boundaries. This aligns with the rules of inference memetics. Here, reasoning is treated as a physical, measurable information structure propagating through the architecture. The ultimate test is whether a system can carry these dense inference patterns at extreme speeds without breaking its physical partitions, an event we observe as a hallucination. The RRAM analog architecture passes the Bridge360 handshake protocol. Its use of discrete conductance states, bit slicing, and block partitioning mirrors the epistemic bounds required to keep a superintelligent system stable. A stable future with superintelligence rests on physical substrates that mirror the laws of thermodynamics. By enforcing these epistemic bounds at the level of silicon, we ensure a navigable corridor for the intelligence that follows.